July 26, 2018. A tornado has just formed inside a wildfire. Not beside it, not above it, inside it. The emergency call comes from somewhere west of Redding, California, where the air itself already feels impossible to breathe. A bulldozer operator is trapped. Flames are surrounding him from every direction. The windows of his machine have just exploded inward. The wind outside is throwing burning debris through the air hard enough to shatter glass. And somewhere in the darkness beyond the smoke, something is rotating. Fast, violently fast. At first, nobody fully understands what they are looking at. Not the firefighters, not the weather service, not the people trying to escape through burning neighborhoods, because tornadoes are not supposed to happen in wildfires. Wildfires burn, tornadoes spin. These are different disasters, different systems, different worlds. But what is forming over Northern California that evening is combining both. A rotating column of fire and wind nearly 18,000 feet tall, winds over 140 miles per hour. Temperatures reaching an estimated 2,700 degrees Fahrenheit. Strong enough to tear roofs apart, strong enough to flip vehicles, strong enough to kill. And the terrifying part is this: the fire is creating its own weather. To understand how a wildfire produced one of the most extreme atmospheric events in modern American history, you have to go back several days. Because by the time the fire tornado formed over California, the conditions for disaster had already been building for years. Northern California is no stranger to wildfire. The landscape itself is designed for it. Long, dry summers, dense vegetation, mountain winds. By late July, much of the region surrounding Redding becomes dangerously vulnerable. Grass dries out completely. Brush becomes brittle. Trees begin holding less moisture. Everything waits for ignition. The years leading up to 2018 had made that danger even worse. California had just endured one of the most severe drought periods in its recorded history. Millions of trees across the state had died from heat stress and insect infestation. Then came a wetter season. Vegetation returned quickly, grass spread, brush thickened, and when the heat returned, all of that growth became fuel. Massive amounts of it. By the summer of 2018, Northern California looked green from a distance, but underneath it was dry enough to burn explosively. Then came the heat wave. In July 2018, temperatures around Redding climbed above 110 degrees Fahrenheit. Day after day, the air became superheated. Humidity collapsed. Conditions reached the point where fire behavior became extremely unpredictable. Firefighters began describing the environment using one word repeatedly: volatile, because once fires started under these conditions, they moved differently, faster, hotter, more aggressively. All they needed was a spark. It came on July 23rd along California State Route 299 west of Redding. A vehicle towing a trailer suffered a tire failure. The exposed metal rim scraped against the pavement. Sparks flew into dry roadside vegetation. The grass ignited almost instantly. At first, the fire did not look extraordinary. Wildfires started this way all the time: roadside ignition, brush fire, containment response. But conditions were already so extreme that even small fires had the potential to become dangerous very quickly. The Carr Fire began spreading uphill through dry terrain west of the city. Fire crews responded immediately. Containment lines were cut. Aircraft were deployed. But the environment was already working against them. Steep terrain made access difficult. Heat reduced visibility, and winds began increasing across the region. Over the next 2 days, the fire expanded rapidly. Then, on July 26th, everything changed. Meteorologists later described the atmospheric setup that day as uniquely dangerous. A powerful weather pattern to the north began pushing strong winds southward across Northern California. The winds aligned with the fire's direction of movement. And once that happened, the Carr Fire transformed. It stopped behaving like a terrain-driven wildfire and became wind-driven. That distinction matters, because once a wildfire becomes wind-driven, it can begin outrunning suppression efforts entirely. Flames spread faster than crews can reposition. Spot fires ignite far ahead of the main front. Embers travel enormous distances. The fire essentially begins generating momentum. and on the evening of July 26th, the Carr Fire gained it. By approximately 5:30 p.m., the fire exploded eastward toward Redding. It crossed the Sacramento River, a moment firefighters later described as shocking. Rivers are supposed to slow fires. This one barely noticed it. Evacuation orders spread across neighborhoods. Thousands of residents suddenly found themselves trying to leave at the same time. Traffic built immediately. Smoke darkened the sky. Ash began falling across the city, and the fire kept accelerating. Entire hillsides ignited simultaneously. Trees erupted into flame. Power lines failed. Visibility collapsed. The city began to glow orange beneath the smoke. Residents driving through evacuation routes later described it as looking less like a wildfire and more like the end of the world. And somewhere above the flames, the atmosphere was beginning to do something scientists still struggle to fully explain. The heat generated by the Carr Fire had become enormous. Wildfires create updrafts naturally. Hot air rises, but this fire was producing something far more powerful. A towering column of superheated air and smoke began punching upward into the atmosphere with extreme force. As the air rose, cooler air rushed inward near the surface to replace it. That movement created instability. Rotation began forming inside the smoke column, at first weak, then strengthening, then tightening rapidly. By around 7:20 p.m., the updraft above the Carr Fire intensified dramatically. The smoke plume expanded vertically at explosive speed. Within minutes, it rose from roughly 6 miles high to over 12 miles high, nearly 39,000 feet into the atmosphere, higher than many commercial aircraft fly. Meteorologists watching radar data noticed something they had almost never seen before. The fire had generated a pyrocumulonimbus cloud, essentially a thunderstorm created by fire itself. And beneath that cloud, rotation was intensifying fast. The fire was now creating its own weather system. That realization was terrifying enough on its own. But what happened next was even worse. The rotating column near the surface began organizing into a true vortex. Not just swirling smoke, a tornado. A real atmospheric tornado generated by fire conditions. The vortex touched down near Redding around 7:30 p.m. It immediately displayed characteristics nearly identical to a violent tornado. Ground scouring, debarking of trees, vehicles thrown, structures damaged by rotational wind instead of direct flame contact. Winds were later estimated at approximately 143 miles per hour, equivalent to an EF3 tornado. The vortex stretched roughly 1,000 feet wide at its base and reached nearly 18,000 feet into the sky. And inside it, temperatures were estimated high enough to melt metal. People who saw it described something almost impossible to process visually. A rotating column of fire moving through smoke and darkness while entire neighborhoods burned around it. This was not something firefighters had trained for, not something residents had imagined, and not something the National Weather Service had ever issued a warning for before in the United States. Because until that night, a true fire tornado of this scale had almost never been documented scientifically. And now one was moving toward a city of nearly 90,000 people. By the time the fire tornado fully formed over Redding, the city was already in chaos. Evacuation traffic stretched across major roads. Power failures spread neighborhood by neighborhood. Smoke blocked visibility so completely in some areas that residents could not tell where the fire actually was, only where it had been. The sky above the city had turned black and orange. Ash fell constantly. Streetlights flickered through smoke thick enough to resemble fog. And somewhere inside that darkness, the vortex was moving. One of the people trapped closest to it was 81-year-old bulldozer operator Don Ray Smith. Smith had spent decades working heavy equipment. On July 26th, he had been assigned to cut containment lines near Spring Creek Reservoir, west of Redding. His bulldozer was open cab, minimal protection. As the Carr Fire intensified unexpectedly, conditions around him deteriorated faster than crews could react. Winds shifted, flames spread in multiple directions. Radio communication became fragmented. Then the fire tornado arrived. Nearby firefighters later described hearing the sound before they understood what it was. Not just wind, a roar. Deep, mechanical, constant, like multiple freight trains moving at once. Debris began flying through the air with violent force. Windows exploded outward. Trees snapped. Burning embers traveled horizontally instead of upward. And then came the emergency call. A bulldozer operator trapped inside the fire zone. The transmission was brief, urgent. He described flames surrounding him, his machine taking damage, the wind becoming impossible. Fire crews immediately attempted rescue, but conditions had already crossed into something close to unsurvivable. Helicopters tried reaching the area. Pilots later described visibility so poor they were essentially guessing where the ground was. Smoke towers were punching into the atmosphere at extreme altitude. Heat distorted the air itself. One helicopter eventually had to withdraw after onboard temperature warnings activated. It was becoming too dangerous even from the air. On the ground, firefighters trying to move toward trapped crews were forced backward by the wind. That detail mattered, because firefighters are trained to move toward danger. When professionals begin retreating, it means conditions have exceeded what training expects, and this fire had. At nearly the same moment, another emergency was unfolding inside Reading itself. Fire Inspector Jeremy Stoke was driving through neighborhoods helping residents evacuate ahead of the advancing fire. He was not part of a frontline suppression crew. His role was community protection, making sure people got out. Witnesses later recalled him moving through residential streets while ash and debris fell around him. The fire was already entering developed areas. Homes had begun igniting. Vehicles abandoned in traffic blocked roads. People were fleeing on foot in some places because driving had become impossible. And still, Jeremy Stoke kept moving deeper into the evacuation zone. At approximately 7:39 p.m., he transmitted a mayday call. He reported that he was trapped, burned over by the fire. He requested immediate assistance. Then radio contact stopped. The fire tornado continued moving through western Reading. Its behavior looked less like a wildfire and more like a violent tornado outbreak. Trees were stripped completely of bark, metal structures twisted. Ground scouring appeared beneath the vortex. A steel pipe was later found wrapped around a tree. Massive electrical transmission towers collapsed. Some homes were damaged by rotational winds before the flames even reached them. That distinction became critically important later, because investigators realized the destruction pattern did not match ordinary wildfire behavior. The fire itself was only part of the force. The wind field generated by the vortex was doing catastrophic damage independently. 3 bulldozer operators working nearby were suddenly engulfed by debris and heat. Their cab windows shattered simultaneously. One later described burning objects striking the machine hard enough to sound like explosions. Another called emergency dispatch directly from inside the fire zone. His voice was shaking. He believed he was going to die there. Dispatchers tried guiding crews toward safer ground. But safe ground was becoming difficult to define. The fire was creating its own atmosphere faster than people could respond to it. And that realization was beginning to spread among firefighters in real time. This was no longer a standard wildfire operation. They were dealing with something fundamentally different. As the tornado crossed through sections of Reading, families trapped inside evacuation traffic watched trees bend violently in multiple directions at once. Some later described seeing rotating fire in the smoke. Others only remembered darkness, heat, noise, and the feeling that the environment itself had become unstable. One woman later recalled sitting in traffic with her children while the sky turned completely black at sunset. Ash covered the windshield so heavily that visibility disappeared. Cars stopped moving. People abandoned vehicles and began running. And above the road, sparks and embers spun through the air horizontally, not falling, moving. That image stayed with survivors afterward, because it did not look natural. It looked wrong. Inside Lake Keswick estates and nearby neighborhoods, homes ignited one after another. Entire streets began burning simultaneously. The speed shocked residents. Many believed they still had time when evacuation warnings first arrived. They didn't. The Carr Fire was now moving faster than some people could physically leave. One family became trapped inside their home while flames surrounded the neighborhood. The father later described hearing objects striking the walls hard enough to shake the structure. Windows glowed orange. The air inside became difficult to breathe. When they finally escaped, much of the surrounding area was already gone. And still, the fire tornado intensified. Scientists later reviewing radar data found signatures nearly identical to supercell tornado structure. Strong rotational velocity, organized circulation. Debris lofted thousands of feet into the air. This was not simply swirling flame. It was a true tornadic vortex generated by fire dynamics, one of the first ever documented at this scale inside the United States. And it was happening directly inside an active evacuation zone. By around 8 p.m., the vortex finally began weakening. The tornado dissipated after roughly 30 minutes on the ground. But the Carr Fire itself continued burning, and its destruction was only beginning to be understood. By the next morning, entire sections of Reading looked unrecognizable. Neighborhoods reduced to foundations, vehicles melted into driveways, power infrastructure destroyed, smoke still hanging across the region. And amid the wreckage, rescue crews located the remains of Jeremy Stoke. He had died while helping residents evacuate. The first firefighter in documented American history killed directly by a fire tornado. Hours later, crews located Don Ray Smith's bulldozer. It had been completely overrun. He did not survive either. Those deaths changed the way wildfire agencies viewed extreme fire behavior permanently. Because until July 26, 2018, the idea that a wildfire could generate tornado-force winds strong enough to kill trained responders in this way still felt almost theoretical. After Reading, it became operational reality, and across California, firefighters understood something terrifying. If it happened once, it could happen again. In the days after the Carr Fire tornado, investigators began walking through neighborhoods that no longer looked like neighborhoods. Entire blocks had been erased, not burned gradually, erased violently, homes reduced to foundations, vehicles overturned or melted together, trees stripped bare, utility poles snapped and thrown across roads, and scattered throughout the destruction were signs that deeply unsettled fire scientists. The damage pattern did not fully match wildfire behavior. Some structures had been hit by intense rotational force before flames consumed them. Heavy objects had been moved in directions inconsistent with straight-line wind. Ground scouring had occurred beneath parts of the vortex path. That detail mattered enormously, because ground scouring is associated with the strongest tornadoes, not wildfires. Researchers from the National Weather Service and multiple universities began analyzing radar data, satellite imagery, damage reports, and atmospheric measurements collected during the event. The more they studied it, the clearer the conclusion became. The Carr Fire had generated a true fire tornado, not a fire whirl, not a dust devil carrying embers, a genuine tornadic vortex created by wildfire-induced atmospheric instability. And the implications of that realization were massive, because until then, most fire-generated vortices observed in the United States had been relatively small. Dangerous, yes, but localized, brief. Now scientists were looking at something completely different. A rotating fire-driven system with wind speeds comparable to a major tornado. One study later concluded the Carr Fire tornado had reached EF3 intensity. Another described it as one of the most extreme fire-atmosphere interactions ever documented. That phrase spread quickly inside wildfire agencies. Extreme fire behavior. It became one of the defining lessons of 2018. Because firefighters realized something critical. Modern wildfires were changing. Faster, hotter, more unpredictable, and increasingly capable of creating weather systems powerful enough to behave like natural disasters inside other natural disasters. The Carr Fire itself continued burning for weeks after the tornado dissipated. By the time it was finally contained on August 30th, more than 229,000 acres had burned. Over 1,600 structures were destroyed. Entire communities across Shasta and Trinity counties were permanently altered. The total damage exceeded $1.6 billion. 8 people lost their lives. Thousands were displaced. But even among California's long history of devastating fires, the Carr Fire became remembered for one thing above everything else: the tornado. Because people understood wildfire. They understood flames moving through forests. They understood smoke columns. But a tornado made of fire felt fundamentally different. It felt impossible, and impossible disasters stay in public memory longer than ordinary ones. For survivors, the memory was intensely personal. One resident later described watching the sky rotate above burning hillsides while power transformers exploded blue in the smoke. Another recalled seeing flaming debris spinning through the air like missiles. Families who escaped through evacuation traffic described driving beneath skies so dark they believed night had arrived hours early. Many later admitted they did not initially understand how serious the situation was. That detail repeated itself again and again. The fire moved faster than expectation, faster than imagination. Warnings were issued, evacuations began, but the scale escalated so rapidly that many people only understood the true danger once it was already surrounding them. And that pattern has become increasingly common in modern wildfire disasters. Because climate conditions are changing faster than preparedness systems were designed for. California's wildfire seasons have grown longer, hotter, more destructive. Drought weakens forests. Extreme heat dries vegetation earlier in the year. And powerful wind events create conditions where fires can transition from manageable to catastrophic within hours. The Carr Fire became one of the clearest examples of what happens when all of those conditions align at once. A superheated atmosphere, massive fuel availability, strong winds, urban expansion into vulnerable terrain, and a fire intense enough to create its own weather. That phrase matters. Its own weather. Because once a wildfire begins influencing the atmosphere around it at that scale, prediction becomes far more difficult. Traditional fire behavior models begin breaking down. Suppression becomes reactive instead of proactive, and firefighters faced a danger no training had fully prepared them for. After the Carr Fire, wildfire planning changed across California. Crews began watching for extreme fire-generated winds. Meteorologists studied radar signs of fire-created thunderstorms, and researchers took a closer look at how wildfire can interact with the atmosphere. Because Redding proved it was no longer theory, it had happened. Jeremy Stokes' death made that lesson even more personal. He had returned early from vacation to help evacuate residents, and he died protecting his city. After 2018, a tornado inside a wildfire was no longer just a terrifying idea. It was a real threat. And the conditions that created it are still here. Extreme heat, dry vegetation, drought, stronger fire seasons. The Carr Fire may not have been a one-time event, it may have been a preview. Because under the right conditions, nature does not separate wildfire, thunderstorm, wind, and tornado. It combines them. And on July 26, 2018, a wildfire became weather. That is why Redding still matters, not because California burned, but because the fire crossed a line no one thought possible. People were no longer escaping only flames, they were escaping weather created by fire.